Welcome.
You got this?
So, going to be here talking about Akka.NET with F# tonight. Thank you very much for coming along and watching me make a fool of myself. So, Akka.NET with F#, this is me. That's not a real book. Yeah, so I'm an independent software engineer, came to Sydney about a year ago from Bristol, UK. I'm interested in these things currently, and you can find me here at ForLoop on Twitter, and also my blog there as well. And in usual tradition, this is my first computer, classic Acorn Electron, 1983. Is that 31 or 32 kilobytes of RAM, I think it was, with classic titles such as Magic Mushrooms. That was the Grand Theft Auto of its era, with a hippie twist. So, let me just bring up my speaker notes so that I can figure out what I'm going to be talking about. So, welcome to the future. And that future is agent-based programming. It's aka the actor model. So it's a mathematical model of concurrent computation, treats actors as the universal primitives of concurrent computation. So in response to the message they receive, they can make local decisions, they create more actors, they can send more messages, and they can determine how to respond to the next message received, i.e. they can change their behavior. And this was all first proposed in 1973, so when I told you the future, I was a little tongue-in-cheek there. So, let's take a step back a second, and let's think about what an agent-based programming is. So in our typical scenario, we're writing our application, sequential flow, so we send an input in, it goes to one component, goes to another component, goes to another component, there's one entry point, other components are called, control, proceeds, and we get a result out at the end. And if we're a little bit smart about things, we can introduce some parallelism there as well. So any work that can be split up and parallelized, we can then perform those in parallel. We can improve the throughput over the sequential model, but ultimately the coordination of this model is the same as sequential flow, i.e. there's one input, do some work in parallel, we'll get an output out of it. So what is the agent-based actor flow all about? Well, communication through each of these nodes here, which we might consider to be actors, is all asynchronous. So the asynchronous message passing between all of these, i.e. they don't block, they don't wait for each other, they send a message and then they carry on and they process another message and they send that one. They don't wait for any replies, they don't wait for each other basically. This is basically the foundation of a reactive system. So we can see that there are some improvements here of the parallel flow model. There could be multiple entry points into the system. Basically, the system is able to coordinate and perform more work, or not more work, but the system is able to perform work more concurrently than the parallel flow. So, kind of probably the most famous example of this is the Ericsson 301. So, it's an actor architecture. It's written in Erlang. So, it managed to achieve in a lifetime it's been running 99.99999% uptime, 9 nines, and that is over 20 years. So this is not individual machines here, this is the overall architecture, the overall service uptime. And for those doing the maths there, that is 0.631 seconds of downtime per year for that system. So pretty phenomenal. Will you let that sink in for a minute? Which brings us nicely on to Akka. So what is Akka.NET? It's basically the JVM, it's a port of the JVM Akka toolkit from JVM over to .NET, and Akka itself is heavily influenced by the actor model implementation in Erlang. And to give you a flavour of who's using Akka right now, all of these big guys are using it. I think William Hill using it for back-end betting systems. I believe LinkedIn are using it for back-end data analytics. It's quite ideally suited for any kind of system where you need low latency and high throughput. And very briefly, it's worth mentioning, as I alluded to before, that Akka is a reactive system, and it's subscribed to something called the Reactive Manifesto. Now, I won't go into too much detail about this because there's a bit of controversy around exactly what is the Reactive Manifesto. Do we really need a Reactive Manifesto? You're just stating the obvious there. But basically, what it is in a nutshell, it's a formalism of systems that we are building nowadays. That the requirements for them have changed. Users expect millisecond response times. System may be distributed over multiple machines. So basically our ability to respond in time for that to scale in when it's under load, and to respond even if the system's at breaking point, at least respond in some way, and be able to scale up and delegate errors as messages as well. So these are kind of the 4 tenets of the Reactive Manifesto. So message-driven, all messages between components are asynchronous and non-blocking, and that aids in elastic, for the system to be elastic, which allows it to scale up and out in response to load. That also aids resiliency as well, so stay responsive in the face of failure. And contain those failures to particular parts of the system as well, so they don't spread like wildfire, jump all the way up to the top, and your app domain ends up falling over. And all of those things help keep the system more responsive. So that brings us nicely on to starting to talk about Akka. Akka is actors everywhere. Pretty much everything in Akka is an actor. Loggers are implemented as actors, dispatchers are actors. Basically, most of the components you can think of in the system are actors. So what does an actor actually look like? So an actor has a mailbox. It actually has an actor reference to that actor. So you don't have a direct reference to the actor, you have a reference to work with, which will allow you then, via some kind of transport, so it may be in memory, it may be TCP to another system, and to deliver that message to a mailbox. So each actor has a mailbox. That actor can also contain state. It has some behavior as well. So it is able to change how it responds to particular messages. And it can also create other actors as well. So this actor can have children, and we can define how this actor then handles those children and supervises them. So actors can receive messages, they can respond to those messages, they can change their behavior to those messages, and they can create other actors and supervise those actors. And I like to think of this happening in a loop. So an actor receives a message from its mailbox. It does some work, whatever that work is in that particular context, and then it returns around and receives the next message off of the mailbox. So this is how Akka is able to handle concurrency, is that the internal state of this actor works in such a way that it only handles one message at a time, and therefore working inside of this actor, you don't have to handle and deal with concurrency yourself. You're entirely thread safe to deal with those messages in whatever way that you need to. So if you need to mutate state inside of the actor and keep its state internally, that's absolutely fine with Akka. So we've talked briefly around what an actor looks like. You might be asking who creates the first actor, and that actually comes from the actor system. So the actor system is a heavyweight object. You generally would create one per process or one per app domain. And when you create the actor system, it gives you this top level actor, which is the root guardian, and then it also gives you the user actor here, the user guardian, and it gives you the system guardian as well. When you start creating actors, they start appearing here underneath the user actor. So you start building up a hierarchy of actors underneath, and each one of these actors has a particular path to it. You can think like a URI, like an address, which uniquely identifies that particular actor. And if you decide, say, to use a different type of logger within Akka, within your actor system, then Akka will create a logger underneath the system guardian there, and any other actors as well. For example, there are other types of actors that get created temporarily, depending on whether you're doing things like a request response, sending a message from one actor to another and expecting a response to come back. That actually gets handled by the creation of a temporary actor that manages that request response pipeline. So that's what the actor system looks like, and you gradually build a hierarchy of actors. So this guy here will be supervising these two guys here, and this one here will be supervising these guys. And this allows you to be able to isolate errors within the system, because each of these actors that supervises its children is able to determine exactly how it handles errors coming from those children. You know, see this type of exception, what should I do? Can I just restart that actor, spin up a new one? Can I stop it? Can it just carry on because it's an error that I don't really care about too much? So you're able to contain errors to particular parts of the system. So going on to creating actors, you've got a few different ways within F# that you can do this. So one of them is to inherit. Can you all see that? Okay, is that big enough? Make it bigger. Let me see if I can do this. Is that working? Yeah. It's just about working. Okay. So you can inherit from a base class, in this case untyped actor, because the messages received here are just the object types. If you were to define the most basic one here, you override the onReceive method, which is going to be called when there's a message available for this actor to process. So the Akka.NET framework itself will handle getting that message to this actor. So you simply need to implement the onReceive method here to decide what you're going to do in response to that message. And then here we create the system. So we use an empty Akka configuration. We give the system a name, which identifies the system, and then from the system we use actor of, and we use props, because actors need props. And we say we want to create an actor of this type of echo actor. We also give it a name here as well, which ends up forming part of the path to that actor. So this actor is created off of the top level. So if you were to look at the address for this actor, it would be in the local system. It would be /user/echo, because it sits just below the top level user guardian. And then finally, we can tell a message to that actor as well. So using the nice F# tell operator there, so we just tell a string message to it, and that actor is going to print it out. But this is all very C#-like. It's not very functional at this point in time. So let's get functional with this. So the F# API provides a few different ways in which we can create actors. So we're F# guys. We like to work with functions. We like to think functionally. So why can't we create a function that expects to receive a message, does something with that message, and construct an actor out of that function? So that's exactly what actor allows you to do. So at the top here, we've got a function here that takes one argument, one parameter, message, prints it out exactly as before, as we saw before. We construct an actor system. Then we use the spawn function. That's the system we want to spawn that actor from. Again, passing it a name for that actor. And then we use the actor of function, which allows us then to pass it a function that takes an object and does something with the object, and returns back a partial function that we can then pass to the spawn system, spawn function, and construct an actor that way. And again, we can tell a message to it. So this is functionally equivalent to what we saw before. To this. Works exactly the same way, although under the covers it's implemented very differently. And we've also got actor of 2 as well, which is similar to what we saw previously, except now we can also receive the actor generic type as well. And what that is the actor that gets constructed by the system via the spawn function. That's kind of the actor that is going to incorporate the function that we pass to it. So we can receive that as well, because we may want to use parts of the actor system, like the scheduler, for example, and we may want to be able to do other things from the system. So we might want to have access to that via the actor type that gets passed to our function as well. So in this particular example, we don't do anything with the mailbox. We only do something with the message, but the option is there. And again, we use the spawn function, and again, we can tell a message to the actor. And finally, the other way that we can create actors is using the actor computation expression. So are we all familiar with computation expressions? In a nutshell, they are a way of being able to build up a workflow for doing a piece of work. In this particular case, so if I take my mouse here, so this is the actor computation expression here. So everything in between these curly braces here is part of the computation expression, and it's basically a way of being able to build up a workflow. And in this particular case, we create a recursive function. Inside of that recursive function, we receive a message from the actor that gets passed in, which is the actor that's going to be wrapping this function. We print that message out, and then we return the recursive function that we've constructed. So it's basically, we're constructing like a continuation in there. And down the bottom here, we initialize this by calling the loop recursive function. So again, we create the actor system using system create, give it a name, give it a configuration, and again use the spawn function here along with the system, an actor name, and our function here that's going to construct our recursive function, and again tell a message to it. Is that all clear so far? Clear as mud? So I can create actors now what? So what can I do with them?
So they're being created on the same sheet at this point?
So right now we are creating those actors purely from the one system. So we're assuming it's all in the same process right now. But to change that such that we construct that actor on a remote machine is really just a configuration change. That's a really good point actually. That I should have mentioned is that Akka.NET, the way it's written is to be distributed by default. So that's everything that works locally can work on remote machines. So there's nothing needed to change. You write your actors the same way, deploy them locally or deploy them to remote machines. So there's a few things that you can do with actors. You pass messages to them, as we saw before. You construct an actor here. Again, we've got an anonymous function here. We again use an actor of. We create an actor. As I alluded to before, it actually returns an actor ref, a reference to the actor, not really the actor itself, but a reference to the actor, which we can post a message to, and Akka will ensure that that message gets to that actor. And again, we can tell a message to it. There's actually other ways that we can send messages to actors and get some way of being able to get those actors, and that's by actor selection. So the F# API exposes a select operator, which then allows us to pass in a path to an actor or actors, because we can target many of this, and pass it to the system as well, and that returns us back an actor selection. So in this particular case, it's going to get us all of the actors that are on the path /user/echo start. So if we'd have constructed, say, an actor called echo 1, echo 2, echo 3, we could use the select actor selection function in order to be able to obtain a reference to all three of those and send a message to all three of them at the same time. So one of the things that's worth mentioning with actor references is that they give you location transparency. So if you can get a reference to an actor, it doesn't matter if the actor's on a remote system, on a local system. If you have a reference to that actor, you have a reference, you can send a message to them. So long as you can get a reference to it, i.e. you could send a message with a reference to an actor in it, then you can send a message back. Similarly with actor selection, if you can pass in an actor path to the select function, you can get a reference to actors. So right now this is only going to look in the local actor system. And if you were wanting to grab actors from a remote system, you would also have to include the protocol that you're using, and so the Akka protocol. You'd also have to be able to specify the transport that you're using as well, TCP, etc. So a few ways you can pass messages that we've seen. You can tell a message to an Akka, that's one way, that's fire and forget. Hopefully it gets there. Akka makes no absolute guarantees of that. There are ways of being able to, on the local system, you would fully expect that message to not be lost within the CLR, and you would fully expect that message to get to that actor. On a remote system, you may be in a less better state. There are ways of being able to put in at least once delivery, so that message gets to the actor at least once, but it may be delivered more than once. There are plugins for persistence and for the mailbox to be able to swap out that behavior in order to have those guarantees if you need them. Other ways are being able to ask an actor. So it's inside of an async workflow here, an async computation expression. You can ask a message of this actor here. So message using the F# ask operator. We get a response back, and then we can do something with the response here. So you can set a timeout for receiving that response back. And you generally probably, as Yoda says, you probably want to tell rather than ask generally in Akka, because tells one way. With ask, what Akka ends up doing is creating a temporary actor to handle that request response pipeline for you. There's a slight overhead with using ask, and it's generally there really to provide you interoperability with systems or protocols that don't handle being able to send a message and then receive one back at some point, maybe in the future. So for example, if you're building a web application and you're dealing with a request response sort of lifecycle then the response is going to wait until you get the response back from the system. So you may be using ask from the back end of your web application to a back end actor system, waiting for a response to come back before you flush the response back to the original cooler. There's also a few other ways that you pass messages. One is using forward, similar to tell, except it respects the original sender of the message. So one of the interesting things about Akka is that when you receive a message from the mailbox, you have the context for who the sender of that message was, so you can send a message back to them. With forward, which you would probably use in some kind of supervisor situation, you may have a supervisor of a child actor, and that child actor maybe is performing some kind of risky operation, so you want to supervise it and perform various actions depending on whether certain exceptions happen. That supervisor may just be the entry point to being able to pass messages to that child actor. So message may be received by the supervisor mailbox, and it just simply forwards that message on to the child actor, respecting the original sender of that message. And there's probably one more that's worth mentioning, and that's type 2. So inside of the receive body of an actor, we might need to do some kind of asynchronous work. So if you're performing some kind of I/O operation, you don't really want that actor to be sort of held up before it can receive and handle the next message. So you may decide to use an async workflow inside of that receive method. And what you can do is pipe the result of that async flow. You can pipe the result of that to a particular actor. So there's a couple of pipe 2 operators there, pipe forward and pipe backwards. So I kind of talked about message passing, what an actor is, what ways you can pass messages to them or handle messages. So what about the hierarchy of actors? So that brings me on to supervision. And so with supervision, you can have one actor supervising one or a number of actors. And I just want to show you with some code examples how that might work. So we've got a custom exception here. We've got a discriminated union for a message. So the message is either an echo of a string or it's a crash message. So we construct the system. Then we have our child actor that's going to be supervised. So build up a recursive function. That child actor receives a message from the mailbox. If there's a pattern match on that message, if it's an echo message, we simply write that out. And we return, we simply construct a response and return that back to the sender of that message. If it's a crash message, we say we're going to crash and we raise an exception. And this is the parent actor that's going to be supervising that child. So the parent spawns the child actor. So there's a reference here to the previously defined child function that's going to construct our child actor. And then we've got the recursive function to define what our parent's going to do. So it receives a message from its mailbox, forwards that to the child, and then it returns that loop back out. So it basically continues, it carries on its continuation. So when we construct that, what does it look like? So we use another spawn function that allows us to pass in some options for when we construct our actor. So spawn opt allows us to pass in a list of spawn options. So again, we use the system, we give our parent a name, we pass in our parent function, then we pipe into that a selection of, a list of spawn options. And what we're saying here is we want to construct a supervisor strategy for this parent to say that when a when an exception is raised, match that exception. If it's like a custom exception, I want you to just restart that actor. Anything else, I want you to use the default supervisor strategy, which is, I believe, to escalate it up to its parent, so the parent would escalate it up to its parent, which if this was sitting at the top level, it would pass it up to the user, user guardian. So if we were to run that, we can send a bunch of messages to the child. That's all good. Send echo messages, send a crash message. It's going to blow up, and then it's going to be restarted by the parent, and then continue again. So there's a few different supervision strategies that you can use. One of them is one-for-one, i.e. Chesney Hawkes, the one and only. So basically, if you have a parent supervising a child, and that child, something happens to that child, what the parent decides to do in that particular case, or the supervisor decides to do, only impacts that one actor. So if it's supervising many actors, it's just that one actor it's going to deal with. And in contrast to that, we have all for one and one for all. And this is basically for situations where supervisors supervising many children, something goes wrong with one of those children, that supervisor needs to take action now for all of those children. So it's kind of applicable. It's kind of applicable in cases where you have sort of tight dependencies between what those children are doing, and if any one particular problem happens, you basically need to abort the whole thing, or maybe in some way. So you need to kill off all the children, and or maybe you need to restart all of the children. So that's the other strategy, which is all for one. And then there are a few different directives that you can decide that the supervisor can do as well. So first one here, escalate. So there's a problem happen, I don't know what to do, I need to pass it up to my parent actor, I'll let them decide what to do, and then it will invoke their supervisor strategy, and they can decide then what they're going to do there. Play, i.e. resume, so carry on as if nothing happened. That message goes off into the ether, maybe it wasn't that important, I'm just going to continue on my merry way. Restart, which is, that child actor then goes through a process of being stopped. There's some hooks there for you to do things when it's about to stop, after it's stopped, when it's going to get restarted, and after it gets restarted. And then finally stop. Just wipe that child out, and that is it. Don't do anything else. Just stop them permanently. It's useful to, or I should point out that restarting clears out the accumulated internal state of any actor. So you need to be careful about restarting. There are ways of managing that with persistence plugins. But let's assume that we're running with the default configuration, and it's all in process and everything is in the application memory space, then you're going to lose the internal state of that actor. Whereas resume here obviously keeps the internal state. In addition to supervision, which works great when you have that hierarchy of actors, you might have an actor over here in the system that needs to know about when things are happening to an actor in another part of the system. So that's where Lifecycle Monitoring comes in, aka also known as Death Watch, similar to the Night's Watch from Game of Thrones. That's all they seem to do in every episode. So with Lifecycle Monitoring, what you can basically, you're subscribing, or you're monitoring the state of another actor, and you can be notified when that actor is terminated. That is basically what you'll receive a terminated message into your mailbox when the other actor is terminated, and you'll have a reference to them, so you know what you can do with them as well. There's a couple of methods for doing that. Monitoring, here's my target, I'm the watcher, and you can also view monitor that actor as well. So If you want to create groups of similar actors, or you want to be able to achieve a better throughput, there are actors within the system that allow you to do this. They generally come under the name writers. There's a few different ones within the system. You can probably guess what they do. Round robin. So if you set up a router actor, you can say to it, hey, I want you to create 10 children that perform this particular action in their receive method. I want you to create 10 of those, and I want you to distribute messages that come to the router to those children in a round robin fashion. So that's how you can increase throughput in the system. Broadcast allows you to have a router that receives a message and then broadcasts the same message to all of its children, all of its routines. Consistent caching is an interesting one, which is worth mentioning, and that allows you to be able to send messages that have particular properties or attributes to the same actor. So you may have 5 routines underneath a consistent caching router, and one of those routines may be interested in messages for the suburb of Darlinghurst. So those should all go to that actor. So you want to use a consistent caching router there. The consistent caching part is an interface implementation on the message, where you define how what the hash should be for that message. And there's a few other ones there as well. And there's a couple of different ways of creating routers as well. We've got pools and groups. Pools allow the Akka system to construct the routines, and there are ways where you can also, via configuration, tell the Akka system to scale those number of routines up, scale them down, what the threshold should be for when they scale up, how many messages in a mailbox, for example. So you generally are letting the Akka framework handle it for you with groups. And with groups, you construct the actors ahead of time, and you pass the paths for those actors to the router, and the router will then send messages to those actors using actor selection. So that allows you to kind of scale up and also out as well, because you can deploy routers to remote systems as well. Oh, I'm going to run out of battery. I've got a charger. Hold on, sorry, one sec. So scaling out, what's that all about? So it's a different one, I think. So Akka Remote is really the magic that allows us to scale out. And it really is just a couple of additional assemblies and a configuration change. So in this particular instance here, let's see if I can keep talking and plug in as well. In this particular instance here, we define a configuration here. So this is using something called HOCON, which is really just a kind of user human optimized configuration object notation. It's a bit of a mouthful, but it's really largely like JSON, but without all of the double quotes, without all of the commas. It's just a way of being able to define configuration. So here we construct the configuration. We tell it what the deployment option is. So for our actor at this path, I want you to be remote deployed to this other system. Let's scroll this down a bit. So down here we construct the system, we give it a name, and back up here, I want you to remote deploy the actor at path my actor to this remote system. This is going to be the provider for how you decide you can get a reference to that actor when it's deployed there, and I want you to use the TCP transport for that. So down the bottom here, again, create the actor system, use our configuration defined here, and then construct an actor, some actor, which I haven't defined here, but let's imagine it's a type that implements Untitled Chapter, pass it the path. This is going to use the configuration here to now remote deploy this actor to the system at this endpoint. So it's pretty powerful stuff. It's simply just a configuration change to go from local deploy to remote deploy. So one of the interesting things here is that this type here would need to be in a shared assembly, so shared by this system that's doing the deploying and the deployed target. So that's one way of doing it, but we can go better with F#. We can use F# quotations to deploy actors as well. So at the top here, again, create an actor system. We use a different spawn function here, spawn E. I'm guessing the E is for expression. Pass the system in, pass a name for the actor, and then we pipe into this a function which is wrapped as an F# quotation. So an anonymous function here wrapped as a quotation, and we pass in a list of spawn options here. So we say we want to deploy this one to a remote system, and that remote system lives at this endpoint here. So with F# quotations, there are no shared assemblies for this. We can take that entire function that's been defined in this one system and remote deploy it to a remote system with no shared assemblies. There are some caveats I should mention to the way in which this works. The code, there's certain caveats around the F# quotation in terms of referencing things that exist outside of the quotation. You need to have things generally inside of there, which kind of is not ideal because it can make things a bit more bloated, and obviously you can't define types instead of quotations. But it's another option nonetheless. And in case anyone's interested how that actually works, the last meetup that we had was Embrace, and those guys there wrote FS Pickler, which is a binary serializer that is able to serialize types. And F# Akka uses FS Pickler, that binary serializer, to take that function and references to serialize it in its entirety and send it down the wire to the remote system, unpack it at the other end, and start that actor. So changing actor behavior, so modifying the state of the actor in response to messages it receives. That's done through FSM, not the flying spaghetti monster, although that would be amusing. It's actually done through implementing a finite state machine in F#, and the way that we can do that is rather nice, using mutually recursive functions. So we can define 3 recursive functions at the same time within F#, and then initialize what this actor is going to do. So it starts with loop 1, receives a message, returns loop 2, receives a message, returns loop 3, etc., etc. And we could also initialize this function with some state that we need to also handle inside of that actor as well, and then simply pass that state through to every recursive function call. So that's quite a nice way of being able to change the behavior, because we can decide what we do in each one of these recursive functions in response to a message. So enough of the warbling. You want to see some examples, don't you? Okay, I'll just start up Visual Studio, which crashed on me earlier. So let's start with what should we start with? Let's see if so that's going to work. Let's start with constructing using the type. So here, inheriting from actor, which provides implements some additional interfaces on over the top of Untitled Chapter is an ability to, I think it implements an ability to stash messages temporarily if you're performing some work. Maybe the behavior of the actor is such that you can't handle messages right now, but you want to stash them until the behavior changes so that you can start pulling them again. So you can take them off, they'll be pulled off of the mailbox, and then you can temporarily stash them in the stash and pull them off at a later time. So that's what the actor type here implements. So if we run this one, so yep, we've got our actor, and then let's send a message to it. Hey, hello, F-sharp Sydney. You can get a bit more F-sharp like here, and use the tail operator as well. There we go, and also send that one through. And again, hello, F-sharp Sydney. So let's move on to the next one. So yeah, so using actor op here, again, similar sort of deal. That's that one. Here. So using actor op. So constructing an actor system, creating an actor using our function defined here, and again, a message to it. Exactly the same as we saw before. Not very interesting stuff. Let me see if I can make things a bit more interesting. Here we go. So using actor of 2 here, so we have a reference to the actor that is constructed. So constructing this actor system here, the function here that takes a value as well as the actor that is constructed, as well as a message it's going to process as well. So just print out the path for the actor itself, and then what we do here is we use the actor to pass in to get the actor context, to get a reference to the actor system here, in order to get to the scheduler in the system. And then what we're going to do here is wait 500 milliseconds, then every 1,000 milliseconds we're going to send the message that was passed to this actor to another actor, and tell it came from this actor, the echo actor, and then we're going to cancel that after 10 seconds. So here's our repeater function here that's going to become our repeater actor, and that just simply prints out the message it receives. So first of all, construct a repeater actor using actor of 2, and then inside of here we partially apply our echo function here, which takes another actor. So we pass it to the repeater actor, and then we pass that partially applied, the result of that partially applied function to actor of 2, so the signature then matches what actor of 2 is expecting to receive, and we give that actor a name of echo. So we would expect, if we were to send a message to echo actor, we would expect it to send that message 10 times to the repeater actor. And just to demonstrate that this is these messages are passed asynchronously and non-blocking, if we send both of these messages at the same time, you'll see them coming through to the repeater. Okay, so jump onto the next one. See what else we've got here. So using our actor computation expression, we've got hopefully a slightly more interesting example here. So again, we construct the actor system, and we've got a actor here that's able to count words. So inside of here, so we define this actor with an anonymous function that takes the actor that's going to get constructed and defines a recursive function that takes a dictionary, receives a message from the mailbox, splits that message into words, increments the counts for each of those words, and then prints out the counts for each of those words. And then we return, we pass the dictionary back into the function that we're calling recursively get. And then we initialize this actor by passing it a new dictionary. So this is simply going to keep the state within the dictionary that is passed to the recursive function. It's going to keep the state of how many times it's seen each of those words. So if we start this one off, we initialize that one. So this sharp interactive window a bit bigger. So we send this message here. So, that's one time, that's one time, simply one time. Let's send a few messages and see what we get. So we can see here that it's keeping the state for how many times it's seen each of those words within the message. And we can keep going, so on and so forth. So relaying that back to, well, what if there was a problem with this actor and it crashed? You would lose that internal state there unless you were using Akka persistence and had some persistence for being able to journal and persist the state of that actor at particular intervals, such that when that actor was reconstructed, it could reinitialize its internal state. So let me see if I've got some other examples here. Feel free to ask any questions as well. I'll do my best to.
How does the persistence there work?
So there are a few different plugins for that right now. There's one for Cassandra, one for SQL Server, one for Postgres. The way that works behind the scenes is through actors, funnily enough. There are, I'm sure someone probably knows more about it than I do in the audience, but from what I understand, if I can remember correctly, is there are regular intervals that you can, say, take a snapshot of the internal state of this actor. It goes to I believe this is for actor state. I could be getting confused with mailboxes, but it goes to a journaling actor that then persists that state and keeps persisting those incremental snapshots of what that internal state looks like. And then at particular points in time, sorry, that's the journaling side, and then at particular points in time, you can take a snapshot such that you don't have to replay the whole original, all of the increments to the state. You can start at a snapshot and then simply replay the journal from that point onwards.
Alright, thank you for the question, Mitchell. Any useful patterns, like a Walmart or any of the information, like here with the command, well, this is how we use it.
Yeah.
These are these class perfectly into whatever.
That's a very, very interesting question, and the patterns for Akka right now are, I mean, there's in the Scala world, there's quite a rich body of work out there for how to build those patterns. There are a few books which I've got some links to at the end, which are pretty have been useful, but most of them right now are in Scala world. There is a book, funny enough, from Manny that's in the pipeline for Akka.net, but it's very early stages right now. So let's have a look at. Let's have a look at ask, and then we'll we'll jump on to some Akka Remote stuff. It will get you really excited. So here, I've just got a calculator actor. There's some operations it can perform. So it's going to receive a message, and then depending on what it receives, it's going to perform the operation and send it back to the original sender. So down the bottom here, we want to, we can basically get the response. We can ask the actor to receive the response for it, and then print it to the console. So we just start this one first. And then we ask some messages of the actor. Hopefully we get back the results that we're expecting. And the same, 15 minutes later, so on and so forth. We've got a slightly more interesting example of that. Using type 2. So similar to last time, same kind of operations, but now we're returning back a result now, what the original operation was, what the output of that operation was, and how long it took, which we've just dummied up here with an async workflow and an async sweep. So we run that async workflow and then pipe it back to the sender. So we run this one. And then I'll look at some here. We construct our calculator actor. Sorry, we define the function for it. Just move this over a little bit so you can see what I'm constructing. So so we have a calculator actor that receives those messages, sleeps for a bit, returns a response asynchronously, and then we also have another actor here that we can send a message to. If it's an operation message, send that onto the calculator. If it's a result message, which is going to be one coming back from the calculator back to our calculate, then we are going to print out the result for that. And if there's any other type of message, we're going to say it's unhandled. So we've got our calculator here. One calculate actor, another one here, and now let's alternate sending a few messages to those actor refs. So there's a random, should have said there's a random sleep for how long these are going to wait. So what I wanted to highlight here is that this is an async workflow inside of an actor that's going to sleep for a random amount of time up to 5 seconds, and then it's going to pipe the result of that async workflow back to the original sender. So if we run these, we may not get them back in the order in which we send those messages. So scroll it over a little bit. So we ended up seeing that the exponent came back, or one of them came back first, followed by other ones in a random order according to how long that operation slept for. And just to show you what actor selection does there as well. So we've got calculate 1, we've got an actor at that path, /user /calculate 1. We've got an actor at /user /calculate 2. So So we can use actor selection using the select operator. We can get a reference to both of those and send them both a message. So yeah, so calculate one, select for this amount of time, turn the result, and calculate two, select for that amount of time, and the result you expect. Let's have a look, see what else I have. Monitoring, I will probably skip that. Supervisor, right. Let's have a look at this one. So, I talked about supervision in the slides. So that was basically this code here. So just to recap, we have a function that's going to be the child actor that sets up a loop that's going to echo out messages it receives unless it receives a crash message, and it's going to raise a possible exception. We have the parent that's going to spawn that child, and any messages it receives is going to forward them on to the child. And then we have our supervisor strategy down here. If it's a custom exception, restart the actor. Otherwise, take the default action. So if we just load that one up. So down the bottom here, what we're going to do is we're going to ask an echo message, pass it to the parent, get the response back, then send it a crash message, and introduce, that should be an instance. We'll forget that for a moment, but introduce a bit of a delay, and then we're going to send another message to the parent child. So basically just demonstrating that in response to this crash message, the child has stopped, has been restarted, and then we can send it another message again. And what we will also see here as well, in the F# API, anything that happens, anything that's going to happen here is going to happen, is going to run before this actor starts. So it's like a pre-start hook, and anything that we want to run after this actor is stopped, we can use this defer function here, and then we can pass it a function, or we can pass it a function that returns a unit to perform some work when the actor is stopped. So we should see these printed out as well when we run this and when we send it a crash message. So we'll have a look at what this does. So you can see it received the first message, hello world, then received the crash order, it was stopping, which was in our defer function there, and then it reran the child started, it printed out child started again, which you can see is this happens here before running the recursive function. And again, we can, just to demonstrate it's all okay, we sent another message to that child and it's absolutely fine. It's received that message and written it out. Let's jump onto something. Do you want to see round robin routers? Yeah, we'll do that one, and then we'll touch on remoting. So the routers are pretty cool. In fact, you don't need to write any code for them. You write the code for the routing, and then you spawn, using spawn options, you spawn the router. So in this particular example here, I have my function here that's going to just receive a message, and it's just going to write something out to the console and return. And when I spawn this, I want you to spawn a round robin writer, bit of a mouthful, with 10 routees, where each routee is going to perform this work here. So remember, we're just going to send 50 messages there and see what happens. Let's just reset that. Let's initialize all this. So it really is just configuration to define a writer here. So I'm using a pool here rather than a group. So I want the framework to manage the routees. So let's send 50 messages. And then if we have a look at the paths for each of those actors that's written out, we can see here that it's constructed actors using $A, $B, $C, etc. for 10 here as the names for those routees, as the names for those actors. And you can also see as well that with the round robin tool, it distributed those messages to each of those, to those different routees as well.
It didn't use $A when B through K. So some reason it doesn't like $A.
That's a good question, and I've not noticed that before. Let's send another 50 messages and see if you get a $A.
It's B through K, so that's 10.
So the parent here is Echo Router, so that's sitting just under user. That's a good question, not sure. Don't know. There could be something to it, yeah. And let's get on to the good stuff.
Maybe use supervising. Maybe he creates one that's a supervisor as well.
Yeah. Alright.
Quite possibly. The way that writers are implemented in the framework, although they are actors, the way that they're implemented is actually slightly different in order for performance. The way that the work is ever so slightly different. They're implemented slightly different for performance reasons. Let's have a look at we'll just have a brief look at this. So it's similar to what we had before. We were defining the round robin pool within configuration in our spawn option. Now what we're doing is defining in HOCON configuration what this router is going to do. So we have the path to the actor here. We want to create a round robin pool, 10 instances, and then we can optionally pass in some resizing methods here as well. So minimum 1, maximum 10, and some different configuration for when that writer should resize. So right now with this commented out, this would do exactly the same as what we saw with the round robin pool via configuration. And then we just simply pass in the writer should be constructed from the configuration here that we passed in to the actor system when we constructed it. So let's get on to the good stuff, because I've realised we are going to run out of time. So I'm going to have to pull this over here for a second. And pull this back just so I can access. There we go. So I can access this here. So up here I've got a couple of examples for Akka Remote. One is using a shared assembly and one is using quotations. So we've got a common assembly here. You probably can't see it easily, but it's just a common assembly that has an actor defined in it. Just got something that we can launch both console apps at the same time. And then we have a system here that defines some configuration here and has deployment for a local actor. It's going to be a round-robin router and a remote actor here as well, which is going to have 5 instances, and it's going to be deployed to the system that can be found here. We're going to use TCP for the transport for that. So if we run this one here, before we do that, the other system here simply has configuration to say it's listening on this port, and its name is this, that's transport, and I'm using Akka Remote actor there as well to be able to deal with remote actors. And this system doesn't define any actors in there, but both System 1 and System 2 have a reference to the common shared assembly. So we go and launch this and start both systems. You'll see them here on my screen, but not on yours. Move these over here. Sorry, can't make the font size any bigger very easily. Let's put them around the other way. So System 1 on the left, System 2 on the right. So System 1 is the one doing the deploying. So that's entered to send messages to the local actor, so it's constructing a local actor, send 10 messages there. Okay, and those messages were received by the local actor there. And what happened as well was the same type of actor was remote deployed to the other system. So shared assembly there with that actor in there. It was remote deployed to the other system, and then we sent 10 messages to that remote actor from System 1. And received those on the remote system, and it's printed out in green, just to signify that these actors are on a remote system and not local. So everything happened through System 1 there. I'll shut this down, you'll see something happened. Endpoint disassociated with System 1, but that's using shared assemblies. And if I just show you a quick example of remoting with quotations. So here we have System 1 and System 2 again. This time, however, we're going to deploy an actor to the remote system using a quotation instead. So let me see roughly what I'm going to do here. Got a local actor. It's going to print out to the console. I'm only locking here so that we don't end up switching the colour of the console while all of the actors that are routees under the round-robin router are competing for changing the colour of the console. That's the only reason for that. So yeah, the console here is a shared resource. So we spawn this one, spawn the local one from config, send some messages to it, wait a little bit, deploy a remote actor, and this is the remote actor we're going to deploy. It's exactly the same as the local one, except it's F# quotation, and we're going to deploy that to System 2. And then just to demonstrate F# quotations, we can have an F# actor defined in a shared assembly, and remote deploy it with a quotation as well. So I've just got a shared assembly for System 1 and System 2 here, just so you can demonstrate they can still have shared assemblies and deploy via quotations. So let's have a look, see if we can make sense of this. So again, we've appeared on my screen. That's System 1, that's System 2. So enter to send messages to local actor. Just 10 messages there to the local actors. Okay, so it's just deployed an actor to the remote system using quotations. No shared code deployed that actor in its entirety as defined in system 1. There we go, we can send 10 messages to it. And now just to show you as well that we can also deploy an actor in a shared assembly with F# quotations. We can send another 10 messages to another actor as well there. So in yellow this time. So that's pretty much remoting in simplicity. If we just jump back to the slides a sec. Okay, so I've just shown you through a few examples. We don't really have time to touch on some of the other stuff that's in Akka as well. So dispatchers are they are the components that determine how messages get to your actors. There are a couple built into the framework you can play with, and you can write your own dispatchers to decide how messages get delivered. We didn't really talk about mailboxes, but you can replace the mailboxes with for particular actors, have persistent mailboxes, perform some other strategy for how you work with messages that are delivered to those mailboxes. Akka itself also implements an event stream or an event bus where various actors can subscribe to particular types of messages, and other actors can publish types of messages to the event bus as well, to the event stream. That event stream is only local to a system, so if you need to get messages to a remote system, you need some way of being able to provide like a proxy to that other remote system. So you need an actor that would be listening on your local event stream and pushing those messages to an actor on a remote system that then publishes to that event stream on that remote system. Then we talk about the scheduler, where we sort an action, be able to schedule messages to happen at certain times. Clustering is very much Akka Remote on steroids. That's probably the best way to define it. It's really what we saw there with remoting, but you imagine the system handles the distribution of actors itself, and you can spin up a machine and say, hey, go and join this cluster of actor systems. I want you to have the ability to have some kind of background worker actors deployed to you, so I'll give you this particular role. This is the system of it. Akka is able to do things like understand that a new role for background workers, a new system has come online that can handle background workers and distribute actors from other actor systems that have background workers in them onto that new node and distribute the work in that fashion. I can do some very clever things. I suggest having a read of that. It all happens via a gossip protocol, so nodes understand which other nodes are within the cluster, when a node leaves the cluster, that kind of stuff. We didn't really talk about testing either. Actors are very much black boxes. There are certain, there is a test toolkit to be able to handle them and be able to test them and make sure that they're working in the ways that you expect. And we kind of really talked about persistence and snapshots. We kind of touched on it briefly. But if you need some resiliency and you need some at least once delivery mechanisms for your messages, then I suggest having a read of that as well. In terms of books out there, so as I mentioned before, most of them are for the Scala world. So Akka in Action is MEAP and Mani. Effective Akka is really the design patterns that you were alluding to. You'll find plenty of patterns in there for building large-scale systems. new one here from Vaughan Vernon, reactive messaging patterns with the Akka model. It's basically taking enterprise integration patterns, that classic book, and applying it to the Akka paradigm. So it goes through all of those integration patterns and goes through how you would implement pipes and filters with Akka, etc., etc. And reactive application development, more general kind of overview of building reactive systems. There are some online resources, obviously the Akka.NET documentation. That's good. It's a little bit light on the ground at the moment, which is why I've also put the Akka Scala documentation up there that can fill in the gaps for any of the Akka.NET documentation. There's also a Gitter online chat, and the members of the Akka community are quite active on there, so if you have any questions, they'll be more than happy to answer them. And I've put out Bartosz's blog here because he's the guy that has most of the F# examples for Akka there, so particular mention for him. If you're interested in jumping in, go and have a look at the Akka.NET GitHub samples. They've got an example of Akka clustering on there to build a distributed web crawler, which is really interesting. Ricardo Terrell, he has a GitHub repository of tons and tons of examples of Akka and also mailbox processor as well from F#, basically agent-based programming. So I recommend having a look at that as well, examples of generating the Mandelbrot set and other interesting things. And also Petabridge, Aaron Stannard, one of the guys, one of the core contributors, also has a bootcamp for Akka as well, which is really worth going through as well. Starts from the beginning and builds up as well. That's me. Thank you very much. Any questions?
The one is that say with C#, is there
So yes, probably Ricardo Terrell's examples there. I'm not sure if I have an internet connection. I was just looking for my phone then, but that's probably got the most F# examples in it, and it's quite useful to see how Actor or Actor 2, the computation expressions are working. That's probably the most comprehensive. A few of the examples are, I think, are a little bit rough around the edges, but you get the general gist of it. I think there's a lot of contributors to it, so that's probably the best.
and the C# and F# actually sort of
Yeah, absolutely. The F# API is really just an API on top of the core Akka abstractions, on top of the core library, just to expose it in a way that is more compelling for functional programming. So it's so nice to be able to take a function, wrap it in an actor, and then use it as an actor, or use it as an actor.
This is the bootcamp, but it's the last one. It's in C#, but if you go to the GitHub account, there is a F# branch that has some example.
Yeah, so if you go to that, you'll see most of George's contributions to the F#.
It's not completed, and you don't have instructions for following that. But if you try to do it, so you read the C# explanation and you use the reference and try to do it yourself, at least you have the solution already working there, and you could compare it with you already have.
What's really useful is to go through those examples and write them in a more functional way. So it's quite a nice example to take the web crawler, which is all in C# Akka, take that and transform it into what it could look like in F#.
What kind of throughput does it support?
So on a local system, if we were looking at the Scala implementation, I believe they quote around 50 million messages a second. So there's a really nice example on the Scala Akka. So the .NET Akka side of things is obviously relatively new in comparison, but on the Scala Akka website, there's an example of a company that serves up like the yellow pages for the States, and they had a system that I believe was over 80 servers, and they were looking to rebuild that using Akka, and they re-engineered how it was happening, how it was working, because what they found was most of the time within that system was actually spent serializing information to send from one system to deserialize in another system, and that was most of the time was spent doing that. So they took that 80 server system, replaced it with an Akka system on 5 machines, and had better throughput as well. I believe it was White Pages was the company, but there's a testimonial on the Akka site for that, which is quite interesting. So I'm glad you said that, because I think I have an addendum. So we won't talk about TPL data flow. I can talk about it if you want, but we'll skip that for a second. So yeah, that's what Mailbox Processor looks like, which is built into F# core. So we have a function here that we can pass a function to that's going to receive a message, and surprisingly, it looks very familiar. We construct a recursive function here that has an async flow inside, receive a message from the inbox, and a message out, and return back the recursive function. So the things about Mailbox Processor is you have to have a direct reference to it. So you're not dealing with actor references, you're not dealing with actor selections, you have to have a reference to this particular type. You can't ask the system, hey, give me a reference to this actor that I know exists at this path. It's built on top of an unbounded queue as well, which is important to note as well, because you can potentially end up running out of memory. Whereas with Akka, you can, it's relatively straightforward, and there are known patterns for implementing back pressure. So if downstream your actors are taking longer to process messages, they can, there are ways of coordinating to say, hey, slow down the processing of those messages, and there are ways of in building bounded queues as well. Obviously, some of those messages may end up going to the dead letter queue, but there are ways of managing that within Akka, which Mailbox Processor by itself doesn't expose. Obviously, you can't distribute this thing either. It exists within one process. And it's the messages here are strongly typed as well, which has pros and cons. Whereas within Akka, messages are all type objects. And in the F# API, there are ways of writing functions that expect to receive messages of particular types. But that's kind of like a veneer on top of fundamentally a message received is going to be an object. And there are some challenges as well with Mailbox Processor of being able to interoperate if you need to with C# as well. Trying to interoperate with Mailbox Processor is a little bit tricky. There's a few examples of the Stack Overflow from Thomas Petruchek of how you would go about managing that, whereas with Akka.NET, you have the C# API, you have the F# API, they can communicate with each other. The F# API has on top the FS-Pickler binary serializer for serializing the quotations, but you can use the same serializer for F# and C# and interoperate between the two.
There's a book called Inside Big Guys. It has an entire chapter where there is another level called toolkit. there is like an Akka framework, but on top of the network processor. It's not as powerful as the Akka because it doesn't have all that stuff, but it adds like addressing on top of things and things like that. And the author of that library wrote an entire chapter in that book, and he starts from building this just an actor plane using the network processor, and start adding functionality and getting to some percentage of what the library provides. So it's a good exercise to follow those examples and writing the code, so you realize which are the limitations and what is the value that the library has. And there is a talk from Rachel Days that he talks about reactive systems to the shard and uses that library.
Yeah, it's a really good chapter, that one. I think in the end of it, he builds an agent system on top of this, which incorporates an ETL workflow. So it's quite, it's quite interesting. Definitely worth getting. Probably just for that chapter alone. Any other questions?
What's the relationship between the JVM version of that and CNR?
So that's an interesting question. I believe they're trying to follow it as close as they can. I believe they're trying to port it as direct as they can, but with a .NET flavoring. So I think there are some things that exist within JVM Akka that aren't currently ported or have variations on similar functionality but are different libraries in the .NET world.
And Roland Kuhn, that is the team lead of Akka, a few months ago published in the blog post that Akka Remote was available and that they are actually collaborating and helping the team to get through what they need to know to implement most of the features. The thing is that Akka is owned by a company that is TypeSafe, that is the same company that builds Scala, and it's a huge company. While Akka.net is basically open source, and there is a company behind that is Beta Bridge, that is the one that you mentioned, but it's a company of two guys, so it's much lower. It's getting quite a lot of support from the community.
Yeah, it seems to be getting quite a bit of traction at the moment.
Yeah.
Cool. Thank you very much.